Hey everybody, this is Patrick GMT and I'm partnering with Chegg, and here I'm going to talk about applications of Taylor polynomials. So one of the big uses of Taylor polynomials is we'll use Taylor polynomials to approximate values of functions. So the idea is we may have a complicated function to evaluate for whatever reason. If we can come up with its form as a Taylor polynomial, we can use a lot of times just the first few terms, which are typically easy to evaluate to approximate a value. So suppose that f of x is equal to the sum of its Taylor series. So we can write f of x in this form. And again, that's going to be equal to f of a plus f prime of a divided by 1 factorial multiplied by the quantity x minus a plus the second derivative evaluated at a divided by 2 factorial multiplied by x minus a quantity squared, etc. So just like we said, if we keep finitely many terms of this expansion, maybe I just look at the first 3 terms and use that to approximate. This would now be an approximation to my function f of x. And that's the basic idea. We'll just keep a handful of terms and use that to approximate. So we want to know, one question is, how accurate is our estimate? And for this, we can examine the absolute value of the remainder. So the remainder r sub n of x, that's going to be equal to f of x minus when we use a Taylor polynomial of degree n. So there's different ways that you can come up with this estimate. One thing that we'll use is we're going to use Taylor's inequality to bound the value on this remainder. So it says r sub n of x is going to be less than or equal to m divided by n plus 1, that quantity factorial multiplied by x minus a raised to the n plus 1. So let's look at a simple example and just see how this works. So suppose we want to approximate f of x equals 1 over x squared with a second degree Taylor polynomial centered at a equals 1. So for x and the values 0.9 to 1.1, we want to know what's the maximum error in this estimate. Okay, well, the first thing I'm going to do is find the Taylor polynomial that goes with 1 over x squared. Okay, so we've got that f of x is equal to 1 over x squared, or equivalently, x to the negative second power. Maybe I'll write them both here. So 1 over x squared, or x to the negative second power. Well, the first derivative evaluated, or the first derivative of x is going to be negative 2 multiplied by x to the negative third power, or negative 2 over x to the third. The second derivative of x, well, that's going to be positive 6 multiplied by x raised to the power of negative 4, or 6 over x to the fourth. And I'm going to use one more here. So this is, when we go to find our series expansion, it says we want a second degree Taylor polynomial. So I only need to go out to degree 2 for my Taylor polynomial. But to bound the remainder, we need to look at some larger values. So again, where m was bounded by, we had to look at the n plus first derivative to come up with this f of m plus 1 of x less than or equal to m value. Okay, so let's see here. So it says the third derivative of x, that's going to be, what's that, negative 24 multiplied by x to the negative fifth, or negative 24 over x to the fifth. Okay, so if I go to fill in my formula, again, it says f of x is going to be equal to f of a plus f prime of a over 1 factorial x minus a to the first plus f double prime of a over 2 factorial multiplied by x minus a to the second, etc. So now we're doing our approximation. So f of x is going to be roughly equal to, now notice we're replacing all the a's with 1s, so we would have f prime of 1, or excuse me, f of 1 plus f prime of 1 over 1 factorial, which is just 1. We've got x minus a, which is 1 to the first power, plus f double prime of a, again, which is 1 over 2 factorial. Well, 2 factorial is just 2. Again, x minus 1 to the second power. And that's as far as we need to go because, again, we're just using a second degree Taylor polynomial. So, okay, if I plug 1 in for, so if I evaluate f of 1, it looks like f of 1 is 1 over 1 squared, which is just 1. f prime of 1 is going to be negative 2 over 1 to the third, which is just negative 2. And it looks like f double prime of 1, that's going to be 6 over 1 to the fourth, or 6. So 1, negative 2, and 6. So this is going to be equal to 1 minus 2 over 1 factorial, which is just going to leave us with negative 2, x minus 1 to the first. F double prime was equal to 6. F double prime of 1 was equal to 6 over 2. So that's just going to simplify to 3. And yeah, that's now going to be our second degree Taylor polynomial approximation. So now we're interested in finding the error. Okay, so it says our remainder. Let's go back up here. We're going to use this formula. So it says the remainder, r sub 2 of x, that's going to be less than or equal to m over, well, it was 2 plus 1 factorial, right? We had to take our n plus 1 factorial. And then we look at the absolute value of x minus a, which is to the first power. Again, that's raised to the third. So, and we also have that f triple prime of x, the absolute value of that has to be less than or equal to m over our given interval. So let's try to, we need to figure out a value for m, and we need to bound this absolute value of x minus 1 raised to the third. So let's do that. So notice our interval, right? We were between 0.9 and 1.1. So if x is between 0.9 and 1.1, well, if I subtract 1 from everything, I would have that the quantity x minus 1 is greater than negative 0.1 and less than positive 0.1. But I can put that back in absolute value and say that the absolute value of x minus 1 is going to be less than 0.1. And we needed this just to be, since we're including our interval, let me put less than or equal to on there. I think that would be a little more precise. Okay, so now from that tells us that the absolute value of x minus 1 raised to the third power, that's going to be less than or equal to 0.1 raised to the third power. But 0.1 raised to the third power is 0.001. So now I know this quantity is bounded by 0.001. So the same thing, we're trying to bound our third derivative of x by some number. Well, our third derivative of x, that was equal to, we found that, negative 24 over x to the fifth. So if we put this in absolute value, we'll simply get 24 over x to the fifth, right? We can just drop the negative. And let's see, for values of x, so now we're doing this for values of x in the interval 0.9 to 1.1. So try to think how, we're trying to find the maximum value of 24 divided by x to the fifth for values of x starting at 0.9 and going up to 1.1. Well, to make this 24 divided by x to the fifth as large as possible, I would want to make the denominator as small as possible. Well, since I'm taking that number and raising it to the fifth, I want to use the smallest number possible, which in this case would be 0.9. So we would have that the max value of the third derivative of x over that interval is 24 divided by 0.9 raised to the fifth power. Okay, so now it says that the remainder, now we can just start plugging in everything. It says it's less than or equal to this value of m, which we figured out is 24 divided by 0.9 raised to the fifth power, divided by 2 plus 1 factorial, which is going to be 3 factorial, which we can replace that with 6. Sorry, I'm looking off to the side and just double checking my numbers here. And we also have to bound this absolute value of x minus 1 to the third. But we did that. We said that's at most 0.001. And now if I do the arithmetic here, I'm getting this to be roughly equal to 0.00677. So we've now, we could use this second degree Taylor polynomial that we came up with. If we take any value and plug, if we take any number from 0.9 up to 1.1 and use that to evaluate the true value on the function 1 over x squared, it says that our estimate is at most going to be off by 0.00677. Okay. What are we doing conceptually here? So notice, again, we've had, if we had only kept the first and the second terms here, in this case, we would end up, notice when we kept to the second degree, right, we end up with a parabola. This would just be our linear approximation of our function. So a linear approximation is just a line. So here's my real function, 1 over x squared. So you can see where they're crossing here, since we're doing this at x equals 1. Notice this is just going to be the linear approximation L of x, and that's if I keep those first two terms. Well, what happens if I use my first three terms, and that's where we end up with a parabolic approximation, if you want to call it that. And notice you can see my parabola here. Notice how it's closer to the true graph, which is the red graph. Notice that the green graph kind of hugs that red graph a little bit longer for x values near 1. So it's just saying, again, visually it's showing that if you use more and more terms, it's going to stay closer and closer to the correct graph for longer and longer and longer for values of x, in this case, near x equals 1, because that was our a value. Okay, so finding the Taylor polynomial I don't think is miserable as long as you know this formula. You're just finding derivatives, plugging in your a value, and then just using the formula to come up with the Taylor polynomial. Bounding it can be a little bit trickier. Just use your interval to bound, your absolute value of x minus a. To find a bound on m, again, you're going to have to look at, in this case, we had to look at the third derivative. We were just trying to bound the third derivative, the absolute value of the third derivative, for values of x between 0.9 and 1.1. In this case, it was easy to reason out that we need to use 0.9 because that's going to give us the largest value when we plug it into 24 over x to the fifth. So that allowed us to bound our m. Again, we bounded our absolute value of x minus a, in this case raised to the third power. Don't forget your factorial. And yeah, so a few things to do. I would say, again, finding this value, bounding this value is going to be the thing that'll probably take the most work. But usually for most of these examples, they should give you something hopefully not too terrible to work with.